In this video, we're going to learn how to simplify numbers that are within a square root and identify irrational numbers. To begin, we're just going to talk about some rules about how we can work with square roots whenever we're multiplying things within a square root or dividing. So our first rule is that if you've got the square root of some number, a, and here a and b are just representing some numbers, we'll see later some examples of these problems, but if you've got the square root of a times the square root of b, then that's going to be equal to the square root of a times b. So the way we can think about this is whenever you've got one square root times another, you can combine it to a single square root where you just multiply the interiors. So if we were going to try to simplify the square root of 2 times the square root of 8, then we could write under a single square root 2 times 8. Now we're going to do this multiplication first to simplify this to a single numerical value, then we can consider its square root. So that'd be the square root of 16. And then what square root is asking you is what number times itself could give us this number. And if we think to our multiplication tables, 4 times 4 is 16. So the square root of 16 is 4. Let's go over some of the basic, what we might call perfect squares that would be useful to know. 1 times 1, which we could write as 1 squared, is 1. 2 times 2, write as 2 squared, 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. And then 8 squared is 64. And because of this, we can rethink of this in terms of square root. So the square root of 1, what multiplied by itself gives us 1? We know 1 is. Next, the square root of 4, if we were asked that, we'd think what times itself gives us 4? Well, we know 2 times 2 equals 4, so the square root of 4 is 2. If we were looking at the square root of 9, we would say 3 times 3 is 9, so the square root of the square root of 9 is 3. And this kind of continues. We know from this the square root of 16 is 4. The square root of 25 is 5. The square root of 36 is 6. And the square root of 49, 7. Square root of 64 is 8. Now I'm going to write the next few ones just up to 12. Those would probably be good ones to be aware of. It would help you go through some of these calculations more efficiently. So 9 squared is 81, which would lead us to saying the square root of 81 is 9. 10 squared is 100, so the square root of 100 is 10. 11 squared is 121, square root of 121 is 11. Finally, this 12 squared is 144, so the square root of 144 is 12. So we know how to find the square root of 4, we know how to find the square root of 9, but we might ask ourselves, well, what would be the square root of 6? And this is going to be hard to do just mathematically in our heads because there's no known integer where this integer times itself gives you 6. For instance, we know there's an integer times itself that gives us 4, that's 2 times 2, so we know the square root of 4 is 2, but we don't know any integer where it times itself gives us 6, so this is going to be a decimal. So there's a few things to note. One, there is a square root button on your calculator, and if there's not, you can always rewrite a square root as to a fractional exponent. It's the same thing as 6 to the 1/2 power. And you would type that into your calculator as 6, this little exponent button. Very important that you keep the exponent in parentheses 1 divided by 2. Let's type this into our calculator, either using the square root button if you have it, or by rewriting it as the exponent to the 1/2. And that would be about, these are all the digits my calculator showed me, about 2.45 if we were rounding to 2 decimal places. So keeping in mind those perfect squares, we are going to learn how to simplify the square root of numbers that aren't perfect squares. So like we just saw, the square root of 6, the square root of 20, things like that. We've got some conditions for when a square root is fully simplified. So if you're looking at the square root of 120, the way that you'll know it's fully simplified is if it meets these three criteria. So in our class, whenever we say simplify a square root, these are the things that you would want to check. First, the number under the radical. By the number under the radical, we mean this number. Whatever is under the square root is also known as the radical. So first, this number under the radical has no factor except one that is a perfect square, and our perfect squares were listed here. So there's no factor that's a perfect square. If it meets that condition, the next condition is that the number under the radical is not a fraction. And if it is a fraction, then we need to make sure that the denominator of the fraction does not have a radical. And we'll see this in our following examples. So in the next problem, we're asked to simplify the square root of 42 and then separately simplify the square root of 72. What it means by simplify is make sure these conditions are met. So first, the number under the radical in both cases is not a fraction, so number 2 and 3 do not apply to this situation. We just have to consider, is rule 1 met? So it's saying the number under the radical, in our first example, the number under the radical is 42. And we need to think, does it have any factors that are perfect squares? Perfect squares 1, 4, 9, 16, 25, and so on. If we're unsure about this, then we can make a factor tree. If it doesn't come to mind the immediate factors of 42, you would make a factor tree by thinking, okay, what can we divide 42 by? We might think of 6 and 7. Okay. Now 7 has no factors other than 1 in itself, but 6 could be factored into 2 and 3. And then we would ask ourselves, are any of these factors perfect squares? Since they are not perfect squares, none of them, this is as simplified as it can be. And if we're asked to approximate it as a decimal, we could later type this into our calculator. If we're asked to find the decimal amount to be the square root of 42, do this in your calculator, to be about 6.480740698. Now we'll go through the same process on our next example. Since the number under the square root is not a fraction, we don't have to worry about conditions 2 or 3, we just have to check is condition 1 met, which involves making a factor tree. Why don't you pause this video and make a factor tree of 72, and when you're done, unpause. As we make the factor tree, we see that one of the factors of 72, if I first divide 72 by 2, because it's an even number I knew I could, I would get the term 36. Now 36 is one of our known perfect squares, and we know the square root of 36 is 6. Let's see how we would use this to simplify our radical. I would first begin by rewriting what's underneath the square root. Instead of 72, I think it'd be more helpful to say 72 is 2 times 36, because that brings us to our perfect square. So I'm going to write this as 2 times 36. And now our rule from above is going to come into play, because we know that if you've got the square root of something times something, in this case this is our 2, this is our 36, then you can split it to the square root of 2 times the square root of 36, following the rule for how radicals can be simplified. And the reason this is beneficial is we didn't know the value for the square root of 72, but we could split it into its known factors, the square root of 2 times the square root of 36, and we know the value of the square root of 36. It's one of our perfect squares, so it's just simply the integer 6. This simplifies to the square root of 2 times 6. And now this step is not necessary, but it is a general convention that when you've got a number, an integer, times a radical, you usually write the integer first. And we know that order of multiplication doesn't matter. So we could rewrite this as 6 times the square root of 2, just because that's kind of the common practice. And this is the simplified radical, because we know that the number inside the radical 2 has no factors that are perfect squares. So this is as simplified as we could get without using a calculator to find the decimal representation. So when you're working with square roots, you'll either be asked to find the decimal value, which we saw right here, or you'll be asked to simplify it into the most simplified radical we can make following these steps. Now, when the number inside the square root involves a fraction, it's going to be helpful to know this quotient rule for radicals. If you begin with the square root of one number divided by another number, what this is saying is you can split it into the square root of the top divided by the square root of the bottom. So you can kind of bring the square root up here and then have a separate one there. Let's see this in an example. Following this rule, if we just wanted to apply this rule here, we are starting here where we got the square root of a fraction. And then it says that you can bring the square root to the top number and divide that by the square root of the bottom number. And now we're looking at, well, what's the square root of 16? We know the square root of 16 is just 4 divided by, because it's a perfect square. We don't know the square root of 3. It's not a perfect square, so we would do this. And then the final step, in terms of being fully simplified, this would go to step 3 of our list above. In the example we were just working, we had 4 divided by the square root of 3, but in terms of our criteria for when something is simplified, no denominator can have the radical. So what we would need to do here is multiply by our fancy 1 again. This is a technique that we saw last time when we learned about how to add and subtract fractions. It's important to note that if you've got the square root of 3 times the square root of 3, that's just the value of 3. Okay? So the square root of anything times itself just gives you the number under the radical. So if we multiply the denominator by the square root of 3, through fraction multiplication, this would cancel and just give us a 3 in the denominator, but we can't change the problem. We can only multiply by a fancy 1, so we also have to multiply the top by the square root of 3. That means this fraction is really the value of 1, so we're not changing the value, and we'd be left with 4 square root of 3 over 3 is the fully simplified radical expression. Let's work on these next 2 examples. I recommend you pause the video and work on simplifying this one as much as possible, recalling our perfect squares, applying this rule, and then unpause when you're ready to check your work. First, by applying this rule, we could split the square root to the square root of 36 divided by the square root of 16. And now, hopefully this is coming to mind that these are perfect squares, so we can simplify these radicals. So we know that the square root of 36 is 6, the square root of 16 is 4, so we can simplify our expression before. 6 divided by 4. This is fine. If you want to simplify the fraction further, we know that 6 is equal to 2 times 3. 4 is 2 times 2. The 2's cancel, and this simplifies in lowest terms to 3/2. Okay. Let's turn our attention now to this. We know we could first split to the square root of 3 divided by the square root of 2. And very quickly we would recognize that neither the square root of 3 or the square root of 2 are known perfect squares, so they don't simplify any further. But what we do need to take care of is the fact that the denominator can't keep the square root. So we've got to use our fancy 1 technique that we did over here to simplify. The only way to get rid of the square root of 2 in the denominator is to multiply by another square root of 2, because that would, through multiplication, just give us the value 2. And we know fraction multiplication, top times top, bottom times bottom. But we can't actually change the value here. Since the bottom is square root of 2, the top also must be square root of 2. So that this is really just the value 1. And we would get the square root of 3 times the square root of 2. And now we kind of layer in the rule from before. Whenever you've got one square root times another, you could rewrite that as the square root of 3 times 2. Okay. Now, do watch out here. These 2's cannot cancel because this 2 is actually inside the square root, whereas this one is not. But we could rewrite this as the square root of 6 divided by 2. Since the square root of 6 cannot be simplified any farther, and we have no longer a radical in the denominator, this one is fully simplified. Now, I do want to give a word of caution. The square root of 4 plus the square root of 9 is not equal to the square root of 4 plus 9. What we just saw before is you could say the square root of 4 times the square root of 9 through multiplication is equal to the square root of 4 times 9. Or the square root of 4 divided by the square root of 9 is equal to the square root of 4 divided by 9. These are both true. So you can imagine that the square root can distribute across multiplication and division, but it does not across addition or subtraction. And if you want to verify for yourself, you could find the decimal value here, the decimal value here, and you'd see they're definitely not equal. So do watch out and don't use this kind of expression through addition or subtraction. Now, if we are asked to add and subtract expressions that involve square roots, we kind of want to think of this as a new expression. This is 3 times the square root of 6 plus 4 times the square root of 6. And what we want to think about it is it's measuring the same thing. For instance, if I said I had 3 apples plus 4 apples, we would confidently say, well, you've got 3 of the things plus 4 of the things. That would mean you have 7 of the things, so 7 apples. And the way we should see this is it's saying I've got 3 square roots of 6 plus 4 square roots of 6. So the result should be that I've got 7 of these square roots of 6. So that's how you would add things so long as the radicals are the same. The key thing I want to point out in this example is the number under the radical on each part of the sum was the exact same. We couldn't use that here because it's the square root of 18 minus the square root of 32. Those aren't immediately measuring the same thing. That's like maybe saying 1 apple minus 3 oranges. That doesn't simplify into a single value of those fruits. So whenever the radicals are the same, you can add, as you normally would think. Let's look at how we would deal with this case. First, the square root of 18 and the square root of 32 are not fully simplified based on what we talked about in just the last few minutes of the notes. So I would recommend that you pause the video and separately simplify the square root of 18, simplify the square root of 32 to take out any perfect squares from the radicals, and then unpause when you've worked that out to check your work, and we'll talk about how, in that simplified form, we can add or subtract those radicals. Whenever we're trying to simplify radicals, we first need to make our factor trees. And what we're looking for in the factor trees are there any of our perfect squares. So 18 is an even number, so I just divided it by 2 and got the factors of 18 are 2 and 9. And we see that 9 is one of our known perfect squares. So when I rewrite this through multiplication, the square root of 18 is definitely equal to the square root of 9 times 2. Through our radical rules, we can split the radical into the square root of 9, the square root of 3, and the square root of 9 is a known perfect square, so that simplifies to 3 times the square root of 2. Similarly, for 32, it's even, it divides by 2, and we see one of the factors is 16, a perfect square. Square root of 32 is 16 times 2. The square root of 16 is 4, which we're multiplying by the square root of 2, which can't reduce any farther because it's not a perfect square. That means our original statement can be rewritten as 18 is now this, 3 square roots of 2 minus 32 is now this, 4 square roots of 2. And we see that we're kind of measuring the same thing. It's saying I've got 3 square roots of 2, and I want to subtract 4 square roots of 2. So you've got 3 things of the same measure, and you're subtracting 4 things of the same measure. That means you would be left with -1 of the things of that measure. So this would simplify to -1 times the square root of 2. In this problem, we would have to simplify both radicals first before we can subtract. And since they're measuring the same type of quantity, we can combine them to a like term. Now in this example, we are going to see a word problem that utilizes the square root. Police sometimes use the following procedure to estimate the speed at which a car was traveling at the time of an accident. A police officer drives the car involved in the accident under conditions similar to those during which the accident took place, and then intentionally skids to a stop. If the test car was driven at 30 miles per hour, so that's the speed of the test car, then the speed at the time of the accident, the thing they're trying to predict, is based on this formula. The speed of the car at the time of the accident equals 30 times the square root of A divided by P, where A is the length of the skid mark left at the time of the accident, so maybe think accident is little a, and P is the length of the skid mark in the police test. Find the speed of the car at the time of the accident S to the nearest unit if it was measured that at the accident the skid mark was 84 feet in length, And in the police car test, the police car was 26 feet in length. What we would want to recognize whenever you're working with a formula and there's multiple variables, you want to ask yourself, which variables have I been given? We were told A is 84 feet, so we've been given the A. We've been told P is 26, we've been given the P. And we're asked to find S, which is the remaining variable. We know that we can immediately start calculating this because the known variables are on one side of the equation and the unknown is on the other. Let's substitute this correctly. So A goes in the top of the fraction, P goes in the bottom. Now the entire fraction is under the square root, so 84 divided by 26. And this would be a problem for our calculator. I'm going to write down how you might type this in. If you've got the square root button, we'll do 1 with that. If you don't and you have to type to the exponent 1/2, we'll show that as well. Now, if you've got the square root button on your calculator, you would first type 30 times, and then you would press the square root button. It would bring a square root up. Then you would type in parentheses 30 divided by 26, close parentheses. These parentheses tell the calculator that you've got a fraction inside the square root. Now, if you don't have the square root button on your calculator, but you do have the exponent button, you would do that as follows. The square root is just a symbol that represents raise this to the 1/2 exponent. These are equivalent things. So if we were typing this in without the square root button, but we wanted to use the fractional 1/2, you would just say 30 times. The parentheses shows that this is all together in a fraction. And then the exponent button looks like this. And then you would want to tell the calculator that the exponent is also in a fraction, so you would enclose it in parentheses. Try whichever method, pause the video here, find your answer, and let's round this to 2 decimal places. So we should get this value, and then we round to 2 decimal places. So I look at the second decimal place, and I look to the right. This number is less than 5, so this would just stay as it is, and that would round to 53.92. Now we think about units. Whenever a problem tells us the units, we want to make sure our answer includes it. S is the speed. So it would be the speed of the car, which we know speed of cars, at least in this problem, we're assuming just American measurements. So we would say miles per hour as our answer. Throughout this class, we might see mention of certain irrational numbers. Now, back in our beginning lecture, we talked about how we could distinguish irrational numbers. And at that point, we talked about irrational numbers being like the square root of 7, things like that. But there's other irrational numbers that are so useful and so widely used in mathematics that we give them their special letter representation of pi and e. So when you see the symbol pi, it is representing this decimal. But the interesting thing is that this decimal continues out to infinity, it never ends, and it never repeats a distinguishable pattern. Now, generally, whenever we're trying to work with pi, even though we know it's an infinite decimal, we generally round it to the first 2 decimal places, 3.14, or the fractional equivalent close to that of 22 divided by 7. Whenever you see the symbol pi, think about the fact that it's going to be equivalent to 3.14, and it is one of our examples of an irrational number. Now, one thing to talk about is pi. These squiggly lines mean about is about 22 divided by 7. And whenever we type that into our calculator, we would get that's about 3.142857143. Now, this looks like a rational number, but as we actually compare the decimals, we see that they agree up to the first 2 decimal places, but then after that, they're different. So all this is saying is that the fraction 22 over 7 is very close to pi, but it's not actually the value pi. So pi is not a rational number. No, it's just approximated by 1. Approximated means close but not equal. Let's look to our next irrational number, e. Whenever you see the letter e in this class, it's not going to be a variable. It's always going to be representing this irrational number, 2.718, continuing on. And just like pi, it continues on forever without a distinguishable pattern. But often, just for application purposes in our class, we're going to round e to the first 3 decimal places and think that it's about 2.718. And for both pi and e, there should be a button on your calculator. So I would look through your calculator, and if you don't see it, send me a Canvas message with a picture of your calculator, and I can highlight exactly where it is if it is there. So just be aware that these symbols represent numbers and know about what they represent. So e is about 2.718, pi is about 3.14. Okay. That's what we want to take away from this section, right, for this page.